Mars. What they're not telling you. They tell you Mars is the next step, the logical destination, the place humanity is destined to go next. They show you rockets and timelines and press conferences and billionaires pointing at launch pads. They talk about it like it's a road trip, like it's hard but manageable, like the math more or less works out. But here's what they don't linger on, the part that gets glossed over in the excitement of countdown clocks and landing animations. Getting to Mars might be possible. Getting back is a different story entirely. Tonight, we're going to look at the Mars trip the way an engineer looks at it, not the promotional version, the real version. The numbers, the physics, the biological reality of what it actually takes to send a human being 140 million miles away and expect them to come home. Because there are things buried in the math that don't show up in the animations. And once you see them, you can't unsee them. Let's begin. The distance nobody talks about, honestly. Mars is about 34 million miles away at its closest approach to Earth. That sounds like a number. Let me make it feel like one. The Moon is 238,000 miles away. Apollo astronauts got there in 3 days. It took humanity the most ambitious engineering project in human history to make that happen. 12 men walked on the Moon. All 12 came home. Mars is 143 times farther than the Moon. Not 143 miles farther, 143 times the entire distance. And the journey doesn't take 3 days. It takes 6 to 9 months, minimum, on what's called a Hohmann transfer orbit. That's the most fuel-efficient path we have. Not the fastest, the most efficient. There is no straight line to Mars. You aim for where Mars will be when you arrive, not where it is when you leave. 6 to 9 months in a spacecraft roughly the size of a small apartment, with the same people, every day. No escape, no fresh air, no resupply if something goes wrong. Now, here's the part they skip past in the press conferences. When you arrive at Mars, you cannot simply turn around and come home. Earth and Mars orbit the Sun at different speeds. Earth takes 365 days to complete one orbit. Mars takes 687 days. The geometry that makes a return trip fuel-efficient, called a launch window, only opens every 26 months. That's called the synodic period. If you land on Mars and immediately want to leave, you can't. The window isn't open. You have to wait 12 to 18 months on the surface, then another 6 to 9 months to get home. Total mission time, 2.5 to 3 years, minimum. That is the number that changes everything. Not the distance, the time. The fuel problem they hope you won't do the math on. Here's where it gets quietly terrifying. You cannot carry your return fuel with you from Earth. Let's do the math the way it actually works. A spacecraft carrying 3 astronauts plus 3 years of supplies might weigh around 50 tons, not including fuel. To push that 50-ton payload on a Hohmann transfer from Earth to Mars requires roughly another 50 tons of fuel. So you leave Earth at 100 tons. Now, for the return trip, you need another 50 tons of fuel. But that 50 tons has to travel from Earth to Mars first, which means you need extra fuel just to carry the return fuel to Mars. This is what the rocket equation does to you. It's not linear. Every kilogram of return fuel you want to carry from Earth requires multiple additional kilograms of fuel just to get it there. The numbers cascade exponentially. For a round trip to Mars carrying all your own return fuel, you'd need hundreds of tons of propellant at Earth departure. The Saturn V, the most powerful rocket ever flown until very recently, could send about 45 tons toward Mars. Not enough. SpaceX's Starship is designed to send over 100 tons. Better. Still not enough for a self-contained round trip. So here's the plan. And this is the part that should give you pause. The plan is to make the return fuel on Mars. using Mars itself. Mars has a mostly carbon dioxide atmosphere, about 95% CO2. Its soil contains water ice. Through a process called the Sabatier reaction, you can combine CO2 from the air with hydrogen, either brought from Earth or extracted from Martian water, using a nickel catalyst at high temperature and pressure. The reaction produces methane and water. 4 hydrogen molecules plus 1 carbon dioxide molecule yields 1 methane molecule and 2 water molecules. The water gets electrolyzed, split back into hydrogen and oxygen. The oxygen becomes rocket oxidizer. The hydrogen feeds back into the reactor. The methane is your fuel. Run this process for months using solar arrays or a nuclear reactor for power, and you accumulate enough propellant to fly home. This is called in situ resource utilization, ISRU, and it's the cornerstone of every serious Mars return mission plan on the table right now. Here's what they don't say loudly enough about that plan. We have never done this. Not on Mars, not at scale, not in the conditions that exist on Mars. We've tested components, we've run experiments. NASA's Perseverance rover carried a small instrument called MOXIE that successfully produced oxygen from Martian CO2, a proof of concept the size of a car battery, producing a few grams of oxygen over several hours. Scaling that up to produce hundreds of tons of rocket fuel, reliably, autonomously, on a planet where dust storms can block sunlight for months, where temperatures swing 100 degrees in a single day, where every component has to survive conditions we've only observed remotely, that is an engineering challenge of almost incomprehensible difficulty. And that equipment has to land safely on Mars before the crew arrives, and work for months before they get there, and be ready and full when they need it. Your return ticket home depends entirely on a machine running perfectly on another planet for over a year before you even leave Earth. 7 o'clock, what 3 years in space actually does to a human being, because this part is almost never in the promotional materials. In microgravity, your bones lose density at a rate of about 1 to 2% per month. After 6 months on the International Space Station, astronauts return having lost 6 to 12% of their bone mass. After a year, 12 to 24%. A Mars mission requires up to 30 months of low or zero gravity total. Do that math with me. 30 months at 1 to 2% per month. You could arrive home having lost 30 to 60% of your bone density. The femur, your thigh bone, the one that carries your full weight when you stand, could snap under normal Earth gravity. Vertebrae could compress or fracture. Standing up after landing could be life-threatening. Muscles atrophy at the same time. Your heart, which is a muscle, shrinks. It adapts to not fighting gravity to push blood to your brain. When you return to Earth, it suddenly has to work 3 times harder than it has in years. Blood pools in your legs. Your brain is starved of oxygen. You lose consciousness. Astronauts returning from 6-month ISS missions routinely have to be carried off the spacecraft. They can't walk. And they've been exercising 2 hours every day in space specifically to prevent this. Even so, recovery takes months. Some bone loss appears to be permanent. Now, add radiation. Beyond Earth's protective magnetosphere, cosmic rays, high-energy particles from supernovas and galactic sources, hit your body constantly. NASA estimates a Mars crew would receive a radiation dose somewhere between 300 and 900 millisieverts total. For comparison, a chest X-ray delivers about 0.1 millisieverts. The career limit NASA sets for astronauts is 600 millisieverts. A single round trip to Mars could push an astronaut past their entire career radiation limit. And on the Martian surface, with no magnetosphere and almost no atmosphere to speak of, it keeps accumulating. The people who go to Mars and return will not be the same people who left. Physiologically, neurologically, possibly permanently. That is not speculation. That is what the data from the ISS already tells us, and a Mars mission is 5 times longer than the average ISS stay. The question nobody is asking out loud. So here is the question I want you to sit with. Every serious Mars mission architecture currently being discussed, NASA's, SpaceX's, every one of them, depends on ISRU working perfectly, on the crew being medically survivable for 3 years in deep space, on radiation exposure staying within limits that haven't actually been proven survivable for that duration, on launch windows aligning, on equipment running autonomously on Mars for over a year before the crew even arrives, on everything. Any single failure in that chain, not a catastrophic failure, just a significant malfunction, and the crew has no return fuel, or their bodies can't handle the return, or the launch window closes and they wait another 26 months. Apollo 13 proved what happens when one component fails on a short lunar mission that was supposed to have margin. They barely made it home, and the Moon is 3 days away. Mars is 9 months away. At the speed of light, a radio signal from Mars takes up to 24 minutes to reach Earth, a 48-minute round trip for a question and answer. In an emergency, you are on your own. Ground control can't help you in real time. Every decision, every repair, every crisis is yours alone. None of this means it can't be done. It means it is harder than the press releases suggest. It means the gap between a successful Mars landing and the successful return to Earth is filled with systems that have never been tested at full scale, in real conditions, for real durations. It means the most dangerous part of going to Mars isn't the launch. It's the plan to come home. Mars is reachable. The physics allows it. The engineering is within the scope of what human beings can build. The mission profile exists on paper, and it is not fantasy. But there is a difference between what is theoretically possible and what is being presented to you as imminent and straightforward. The timelines keep moving. The technology required keeps being described as almost there. The biological realities keep getting smaller, type in the footnotes. The people who go to Mars first, if they go in the next 2 decades, will be the most courageous, or the most desperate, or the most committed human beings who ever lived. They will spend years of their lives in a metal cylinder, absorb enough radiation to statistically guarantee long-term health consequences, and depend on an automated fuel factory on a foreign planet to not fail before they need it. And they will do it anyway, because that is what exploration has always asked of the people who actually do it, as opposed to the people who announce it. The question isn't whether Mars is possible. The question is whether you're being told the full truth about what possible actually means. Now you know a little more of it.